Good morning, girls. Children, we are going to complete these two questions from the exercise 1.1 and then I'll take up one example also. Question 4 says that using Euclid's division lemma, show that the square of any positive integer is either in the form of 3m or 3m plus 1 for some integer m. Okay. And they have given one hint that let x be any positive integer which is in the form of 3q or 3q plus 1 or 3q plus 2, and these forms we are going to take like 3q, 3q plus 1 and 3q plus 2, and then we are going to express this in the form of 3m and 3m plus 1. So let us see how will we do. We will start with using the Euclid's division lemma. Question 4. Let a be equal to 3q. Now there are three conditions given. So we can take let a be 3q or 3q plus 1 or 3q plus 2. So one by one we are going to solve this and we'll check out whether we can express them in the form of 3m and 3m plus 1 or not. Okay, so let's do it. A is equal to 3q. We'll take case 1. First case. On squaring both sides I will get a square is equal to 3q the whole square. Okay, now I can write a square is equal to 9q square. Now this 9q square I can write it as 3q into 3q. Okay, now or I can write a square is equal to 3m. Now what is m here? M is equal to q into 3q. Okay, next, this is the first case. Second one is a is equal to 3q plus 1. Case 2. On squaring both sides I can write a square is equal to 3q plus 1 the whole square, which will give me a square is equal to 9q square plus 6q plus 1 using identity. Now a square is equal to, if I look at this, I can take out 3 common and write here 3q plus 2. 3q plus 2. And 3q plus 2 plus 1. Right? 3q common, 3q plus 2 plus 1. Now I can write a square is equal to 3m plus 1. Now m will be over here. In this case, m will be equal to q into 3q plus 2. Right? So we can express a square in the form of 3m plus 1. We can also express it in the form of a square is equal to 3m. Now there is one more case, case 3. In the third case, we are going to write case 3. A is equal to 3q plus what? 3q plus 2, right? Now for 3q plus 2, I will take squaring both sides. I will write 3q plus 2 the whole square, which will be equal to 9q square plus 2 into 3, 6 2s are 12q plus 4. A square is equal to, now I can write 9q square. Now in 9q square plus 12q plus 4, this 4 I can write it as 3 plus 1. Okay, now in these terms 3 is common, so this will be 3q square plus 4q plus 1 plus 1. So here I can write a square is equal to 3m plus 1. Now here what is m? M is equal to 3q square plus 4q plus 1. So it means that any square number, positive integer, can be written in the form of 3m plus 1, can be written in the form of 3m. So this is what we had to prove. So we can see the question again, that any square positive integer can be written in the form of 3m and 3m plus 1, and this is what we have proved. We took A is equal to 3q, A is equal to 3q plus 1, and then squaring both sides, we proceed with the three cases. Okay, so I hope the question is clear to you. Now similarly, question number 5. Euclid's division lemma we have to use, and you have to show that the cube of any positive integer can be written in the form of 9m, 9m plus 1 or 9m plus 8. Okay, so let us take same way. We start with we want now cube here, so we write let, the question is this, let a be equal to 3q. Then we start with taking cube both sides. Then I will take 3q plus 1 and 3q plus 2. So here also in the three cases we are going to prove that these can be written in the form of 9m, 9m plus 1, 9m plus 8, and this is what cube of any integer m. So let's begin with taking cube both sides. I will get a cube is equal to 3 cube the whole cube. A cube is equal to 27q cube. Now I can write this as 9 into 9 into 3q square, and here I write q. Okay, so this is how I can write. So therefore here a cube will be equal to 9 into m, and what will be m here? M will be equal to q 3q square. So that means one cube can be expressed, the cube of integer m can be expressed in the form of 9m. Okay, did you follow? So what we've done, a is equal to 3q. We have to write that cube of any integer m can be expressed in the form of this. Now here in the second case I will take a is equal to 3q plus 1. Taking cube both sides, a cube will be equal to 3q plus 1 the whole cube. When we are talking about square, we will square both the sides, and when we are taking cube, we will take the cube both sides. A cube is equal to 27q cube, this is a plus b the whole cube identity, plus 1, plus now 3 into 3, that is 27q square, plus 3 into 3, 9q. Now I will pick up these terms and group them, and plus 1 will be separate. So I will write a cube is equal to 27q cube plus 27q square plus 9q and plus 1. Now if you look at these terms, you can say that 9 is common. So I will write 9 common. Now what is common? Q is also common. So therefore I will write here 9 3q square plus 3q and plus 1. Okay, plus 1 here and plus 1 this one. Now a cube is equal to 9m plus 1, and what is m here? M is equal to, you can check, m is equal to q 3q square plus 3q plus 1. So I will write m is equal to q 3q square plus 3q plus 1. Coming to the next part, let a be equal to 3q plus 2. Taking cube both the sides, I will get 3q plus 2 the whole cube, and therefore it will be 27q cube plus 8 plus 3 into 9, 27q square plus 3 into 4, 12, 12 3s are 36q, right? Now again I will group them together, 27q cube, 27q square plus 36q plus 8. A cube is equal to, now here also 9q common, yes, it will be 9 3s are 3q square plus 9 3q plus 9 4 plus 8. So again I can write a cube is equal to 9m plus 8, as you can check here. 9m also we proved, 9m plus 1 and 9m plus 8. So therefore, over here value of m is equal to q, 3q square plus 3q plus 4. That means we can express any positive integer m in the form of cube. Okay, in the form of cube. So here we have a cube is equal to 9m plus 8. Here we have 9 a cube is equal to 9m plus 1. And similarly here also it is 9m. That means we can express an integer cube of any positive integer in the form of 9m, 9m plus 1 and 9m plus 8. This was the question in which we had to express the square of any positive integer in this form. 3m plus 1. Okay, then it was 3m plus 1 also in this case, and here 3m. Okay, so these two methods, I think they are quite similar. I hope it is clear to you. Question number 4 and question number 5 complete, and we have already completed 1, 2 and 3. Now I'll take up question number 4, that is example 4 given here. A sweet seller has 420 Kaju Barfis and 130 Badam Barfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the maximum number of barfis that can be placed in each stack for this purpose? So what we'll do, we have how many types of the barfis? We have 2 varieties. Example 4. We have 420 and 130. Now we have to stack them together in such a way. Stack them means we have to arrange them, or we have to we can pack them in such a way that each stack has the same number and the least area of the tray. Okay, both. So what is the maximum number of barfis that you can place in each stack? So to find the maximum number of barfis in each stack, we have to find the HCF. So using the Euclid's division lemma, we are going to find the HCF of the two numbers. So example number 4, the numbers which are given are 420 and 130. So statements, as I told you, it is given that the maximum number of barfis that can be packed in each stack will be HCF of 420 and 130. Now children, as I told you before also, if you can directly do it, you do it. Otherwise you can apply the division method. So we start with 130 and 420. You know that 13 3s is 39, 390, 0. Here you get 40. Okay. This will be 12 and this will be 3. Then 130, 43 is 120, 10, and here I get 40. So 10 4 is 40. So as you can see that the last divisor is 10, we will write therefore HCF is equal to 10, and we will write therefore 10 barfis can be packed in each stack. Now 10 barfis, it can be either Kaju barfi or it can be a Badam barfi. Okay. Yes. So this completes your question number 4. And you know now what is Euclid's division lemma? It is A equals to BQ plus R, in which A is a dividend, B is a divisor, Q is a quotient and R is a remainder. And the two conditions which are to be followed when we are solving the question is R is always greater than or equal to 0, but always less than the divisor. Okay, and then we can proceed it. Now the same question, that is question number 4, I can write it in the other form, that is 420 is equal to 130 into 3 plus 40. Then 130 is equal to 40 into 3 plus 10. Then 40, I can write it as 10 into 4 plus 0. So therefore here the answer is what? 10. So children, this completes your exercise 1.1 and I hope it is clear to you. And revise whatever we have done in the previous part in the beginning of the chapter. Complete all your work. And then in the next video, we are going to start with the fundamental theorem of arithmetic. Okay? So complete all your work. Any doubts you have, you can ask me. Thank you. Have a nice day.